So we've talked about Lewis dot structures and how to draw them, and the octet rule, and single bonds and double bonds and triple bonds, and how hydrogen doesn't obey the octet rule, but there's more. There are 3 exceptions to the octet rule. That says exceptions to the octet rule, where I'm half writing and half printing. And you kind of need to know these two. The first one is something called an incomplete octet. An incomplete octet sounds, or is exactly what it sounds like. It's a situation where you don't have enough electrons to complete the octet around the central atom. It usually happens when you have things in group 1 and group 2 bonding with hydrogen. For instance, if we looked at, let me see, boron trihydride, BH3. We do the skeletal structure with boron in the center. Let's put the hydrogens at their appropriate 120-degree angles. Boron has 3 valence electrons. It's in group 13. Hydrogen, there are 3 of them. So that's going to give you 3 times 1, or 3 valence electrons. Together you have 6 valence electrons. Even with double bonds, you can't make 8 out of 6. So we would be putting a single bond between the boron and each of the hydrogens, and that's it. It's finished. You just can't do any more than that. So we accept that and we move on. The second one is a little bit more fun, actually. It's called an odd electron molecule. Now, if you think about this, if you have an odd number of electrons, somebody's not going to get paired up. It just happens. You can't divide an odd number by 2. So, for the sake of it, let's do NO2. Skeletal structure would give you nitrogen in the center and oxygen on the outside. Nitrogen has 5 valence electrons. 2 oxygens are going to give you 2 times 6, or 12 valence electrons. If we total those up, we get 17 valence electrons. So let's start putting them around here. And I should probably be doing this with a pencil if I can find one. And I can't, so we'll just go on with a pen. Okay. 17 valence electrons, single bond between N and O. In both cases, we've used up 4. We have 13 electrons left. Let's complete the octet for the outer atoms. 2, 4, 6, 8, 10, 12. We have 1 electron left. Okay, let's just throw it on the nitrogen. Each oxygen has 2, 4, 6, 8 electrons around it. 2, 4, 6, 8. Nitrogen has 2, 4, 5. We can do a little bit better than that, but not much. We can get rid of that lone pair, which should actually be erased, but I don't have a pencil. Oxygen still has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 7. This oxygen still has 8. That's the best we can do. You could have chosen either oxygen to remove the lone pair from and make a bonding pair, but in either case, you'd have 8, 8, and 7. Nitrogen, being less electronegative than oxygen, gets the 7 electrons rather than the 8. And the very last one is called an expanded octet. Expanded octets work in elements that have d orbitals. They must have d orbitals available to them. which means they have to be in period 3 or below. And by below, I mean lower than on the periodic table, not a number less than 3. So we could do a really messy one, or we could do... I'm going to do an easy one. Let's do sulfur hexahydride. Sulfur has 6 valency electrons. Hydrogen each has, there's 6 hydrogens. 6 times 1 gives you 6 valency electrons. And the sulfur would be in the middle. We're going to put the hydrogens around the... Whoa, I didn't just do that. Sulfur is in the middle. Hydrogen, hydrogen. A couple more hydrogens as far apart as we can get them. And you're going to have 2, 4, 6, 8, 10, 12. We've just used up all of the electrons. Sulfur, which is in period 3, is surrounded by 2, 4, 6, 8, 10, 12 electrons, and each hydrogen has its 2 electrons that it's happy with. Sulfur is in period 3, so anything in period 3 or lower can do that. Those are the 3 you need to remember. Good luck with that.